Hey gang, welcome back. So we are gearing up for our final unit of the year, which is crazy to think about. So we're going to be looking at organic chemistry. For many of us, and if you notice, we're out of order with the textbook. So this is technically chapter 15 in the textbook. Myself and Mrs. Williams out at North, we kind of decided let's pull it and put it at the end so that if you plan on going on two more chemistry, technically Chem 211 or our AP Chemistry is this tail end of your freshman year of college. You would then go on to take, once successful with this course, you would go on to then take our organic chemistry as your next chemistry course in science. And so we kind of move organic to the end, so it'll be the last thing you see with us, and then it'll be the first thing that you then see going back into kind of your post-secondary career. Organic chemistry is a little bit different. We've alluded to this before. There's not going to be any math here because there's no math to be done. Theoretically, we could, but that's not until like second semester organic. A lot of what we're going to be talking about are going to be just kind of naming, the drawing, and then the basic introduction to our reactions if we have enough time before we need to start preparing for our end of year assessments. And so what's nice about this is you actually have a pretty good foundation in kind of the base organic information. We're just going to kind of layer on top of that with what you already know. That being said, there is a fair bit of memorization here. Please make sure you start with that little sheet that was attached to our last email. Got to start by memorizing those functional groups. Once you've got the functional groups and you got kind of the base naming down, you can do any problem I give you because there's a real nice pattern to naming and writing organic chemistry molecules. Organic, just like it sounds like, it is organic. Okay, what does that mean? We're going to be looking specifically at structures that appear in biological things that are primarily built with carbons and hydrogens. Every now and then you can have other things thrown in there, but that other stuff thrown in there has to be a non-metal. When we start pairing things with metals, it becomes ionic, and we call that inorganic. So our organic chemistry is just dealing with our mostly carbons and hydrogens. Single and double bonds are covalent molecules. What's nice, you've already had a whole class of these that you've already seen in the form of our alkane hydrocarbons. If you remember, that's like pentane, butane, octane, nonane, decane. These are going to be the base structures for all of these molecules. As we start kind of building in, we are just going to trade out some different parts and start to talk about how they bond. Organic molecules as a whole are pretty smelly. They're fairly different than our inorganic salts. Typically smelly. They can be solid, liquid, or gas at room temperature. Going to depend kind of on the molecular size and how they start to interact with their different London or intermolecular forces. Some dissolve in water, some don't. There's a whole list of properties that we can start to describe for these. But the big ones are they're relatively low in melting point. They're going to stink, and we can start to then describe them using kind of their shapes and their molecule names. Like we said, it's going to be mostly carbons and hydrogens, and so our alkane-ane ending means that they're all single bonds. Sometimes we call it a saturated molecule, where every molecule has as many things attached to it as possible. Once you start adding double bonds or triple bonds, we say that is an unsaturated. Saturated, unsaturated fats, which are organic, and they're kind of stinky and can be different states of matter at room temperature. Okay, cool. So let's just real quickly review as we start to name and write our alkanes. Ane ending matches the ane ending for our different examples. If you remember, there's prefixes based upon the number of carbons, but it's going to be whatever the number of carbons are, it's going to be times 2 plus 2 for the number of hydrogens. So if this is our number of carbons, we multiply by 2 and then add 2 specifically for the alkane, anes being all single bonds. All single bonds. Cool. If you remember, the first four are a little different. We kind of don't use the traditional prefix system for the first four, for meth, eth, prop, and bute. If you remember, the saying was me eat peanut butter, meth, eth, prop, bute. So for example, if our name was butane, bute, me eat peanut butter, bute is 4. So it's going to be C4 for, I just put it here. It's going to be C4 for the number of carbons times 2 is going to be 8 plus 2 more gives us 10. It would be H10 would be the actual molecular formula for butane. Could do another one. For example, if we had, hexane. Hexane, hex meaning 6, so it would be C6 times 2 is 12, plus 2 more is 14. If you think about the actual molecule, we can start to kind of draw that. It's going to be a big piece of this unit is actually drawing these organic molecules. If we wanted to draw it, there's a couple different ways we could do it. We could show every single bond. Carbon and a carbon and a carbon and a carbon. So for butane, there's 4 carbons. Single bond between each of them. I need to attach my hydrogens. I'd have on top and on bottom. And then we'd have 2 more. Boop, boop. So this is why the formula is times 2 plus 2. So kind of the times 2 part is the top and bottom hydrogens. The plus 2 part are the ones on the ends. We call this the structural formula where you showed every single bond, every single hydrogen, every single carbon. It's a lot of work. Sometimes we'll do the condensed form or the condensed structural, where you'll sometimes see the CH3, CH2, CH2, CH3, if we're just thinking about kind of the groups that we've got. Sorry, there's a little bit of glare there. I don't know if that helps or not. So this would be the condensed form, but sometimes we don't really care. We can assume there's hydrogens there. It's a lot of work to write all those hydrogens every time, and so sometimes we'll use what's called the skeletal form. And you're going to love this because it's way less work. When we're doing big reactions or big molecules, it's kind of tedious to draw these, and so the skeletal would look a little something like that. And I know what you're thinking. You're thinking, Jorgensen, that just looks like a squiggle. And you are correct. This is our skeletal because we're really just showing the backbone. We're assuming that, since we're not told otherwise, that there's enough hydrogens here to make everything stable. Each point or end of a line would be considered a carbon. So there's 1, 2, 3, 4 carbons, just like there was for butane. Coming off of each of these carbons then would be enough hydrogens to make them happy. You need 3 for this one, 2 for this one, 2 for this one, 3 for this one. But again, it's so much easier just to do 4 little lines than show each and every carbon and hydrogen. Cool, look at another example. Oh yeah, hexane, we did hexane. So it would be 6 carbons all with 1, 2, 3, 4, 5, 6 carbons with then single bond all up and down with hydrogens all around. Or we could do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We would just have 6 little lines to show the skeletal form of our hydrocarbon hexane. Should be able to go backwards as well. I could give you, for example, a formula, or I could give you then a squiggle, essentially. Give me 1 second. So theoretically, I could give you a squiggle, and you could then go ahead and start to tell me what its name would be. Let's do squiggle, 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 squiggle. Sure. Squiggle, 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 squiggle. Count your points. We've got 1, 2, 3, 4, 5 carbons. So let's see, 5 all the way around the outside. It would be enough hydrogens to make it stable. So times 2 plus 2, 10, 11, 12, H12. C5 would be pent. Pent tells us the number of carbons. There's 5 of them. And then we would add the ending ane to indicate that it's all single bonds. We could then draw the structure. It would be 5 carbons all attached with hydrogens all the way around the outside. Theoretically, there are other ways you could do this, right? Couldn't you do this? Ooh, that was right in the glare. That was terrible. Theoretically, you could draw your structure like this, but technically your long chain is still 1, 2, 3, 4, 5 going across. So it is still pentane. We just kind of reorganize the bonds. If you remember, across the sigma bonds, you actually have rotation. These actually could theoretically fold, especially when you start getting into the longer, like octane, the 8 carbon chains. These aren't going to fold around that sigma bond, and so this would still be 1, 2, 3, 4, 5. This would still be a pentane, assuming we've got hydrogens all around the outside. Cool. It's going to be crucial that you remember your kind of hydrocarbon nomenclature. We're going to be using specifically the IUPAC system of nomenclatures for this unit. IUPAC stands for the International Union of Pure and Applied Chemistry. They are kind of the UN of chemistry, of a multinational committee that has decided here's how we're going to name these, so that if you have an IUPAC name, there is only one molecule it could be referencing. And so that's where we're going to kind of lay our foundation and build upon that. Cool, so this is kind of our base introduction to organic nomenclature. If you got questions, feel free to reach out. We'll make sure we're doing okay as we continue to move forward into our organic chemistry.